Okay, it is fine. Let's start today's session. So I saw that you already added one midterm exam. We have total 2 midterm now. You know that the total mid one is completed. So another midterm, I'm thinking that it will be some beginning week of March, okay, after our spring break. Okay, we'll decide later. The no worries now. Okay. It will be first week or second week of April. Should be fine, I think. Okay, then after then I will give you one assignment kind of for your extra credit. Let's see. Later we will also decide that things as well. Okay. And, okay. So we already done. We already studied some memory management. Process management algorithms. Process means that your operating system short-term scheduler actually use these algorithms to schedule schedule the CPU for a specific process. Okay, this is for short-term scheduler. Operating system short-term scheduler use this kind of algorithms. We already learned the LJF shortest job first scheduling algorithms, LRTF as well as FCFS. And in our last class, we talked about the LJF, longest job first scheduling algorithm. From this name, you can also understand that it is kind of opposite of SJF and LJF, which opposite to each other. Okay, and in our today's class, we hope we'll learn some other algorithms for scheduling. Okay, some details. We'll learn some details of some others language, others algorithms. This is LRTF, 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 and another is some priority-based algorithms. And next we'll learn another algorithm's name is SRNN. We'll see the details on it, and also finally we'll learn the another algorithm is round robin scheduling algorithms. Okay, so then actually we can say the end of our processor management systems, and next we'll talk about some about regarding the thread. Okay, we don't learn yet the thread things. Now we are talking about the process. Okay, we know the process block, and also and then actually we start the how your operating system schedule the CPU for a particular process. Okay, so let's start our today's class. So before I start, let me open my PowerPoint slide first. Also, you will find your PowerPoint, all of your PowerPoint slide inside the module. Okay. Also, please learn the especially additional PowerPoint slide that I uploaded for your exam. Okay, next exam. Advanced operating system. And today we'll talk about additional part 2. Here we already know about the LJF in our last class. Okay, we talked about the LJF, longest job first scheduling algorithms, and today we'll talk about the longest job remaining time first scheduling algorithms. Okay, also we talk about some comparison. In our last class we talked about some comparison between LJF, SRTF, and FCFS. Okay, and here where we saw that some effect called the convoy effect as well as distribution problems. Okay, Same problems we saw in memory management systems. You know that any priority-based algorithms may suffer by the starvation problems. Here also you find another effect is called the convoy effect. Okay, this is very important. Yeah, important. You need to know about this. What is a convoy effect? Okay, and then we compare the throughput between LJF, SRTF, and FCFS algorithms, and also we learn the LJF algorithms. Okay, convoy effect is nothing but a process needs to wait for a smaller process needs to wait for a long time. Okay, uh, until actually one big process get off or release the CPU. Okay, this is the convoy effect. Also, you know that if you consider this LJF, longest job first scheduling algorithms, this is also longest job means that it is longest job actually doesn't refer as the size of a process, it refers the execution time of a process. Okay, its longest means that it has longest execution time or burst time. Okay, this is how it is called the longest. Okay, it is not the largest process. Okay, longest job scheduling algorithms actually depend on the largest execution time or burst time. This process will be scheduled first in case of LJF. Okay, from here you can see that this is also a priority based algorithm because it depends on the burst time. Burst time or execution time is this is a property of a property of a process. So it is a priority based. Also, it is non-preemptive as well. LJF non-preemptive means that once you schedule a CPU for a specific process, your CPU cannot preempt or cannot forcefully stop this process. Okay, this is non-preemptive scheduling algorithms. Also, here you can see that if it is priority-based algorithms, what will be the problem for LJF? Of course, there will be the starvation problems because it is priority-based algorithms. Okay, of course, the LJF longest job first scheduling algorithm. So your actually smaller process always needs to wait for until actually execution finished by the actually largest or longest process. Okay, so there we must convoy effects. Okay, throughput is very small, very less. Okay, if it is if convoy effect, if any algorithm suffer by the convoy effect, then throughput will be, of course, will be very less. Okay, and then it is difficult to implement. Difficult to implement means that if you consider the burst time or execution time as a parameters or actually property for to schedule a process, LJF, SRTF, and LJF, it depends on the burst time. Okay, burst time or execution time, and you know that it burst time and execution time is very difficult to compute at the beginning. Once it executes, then you can know the exact burst time or execution time. Okay, that's why at the beginning of when you start a process, you cannot compute the burst time or execution time. Okay, it is very difficult to compute the exact burst time and the computational time. Okay, sorry, execution time. So this kind of process actually it's very difficult to implement. Okay. Okay, so let's jump on our today's algorithms. We learn that is the longest remaining time fast scheduling algorithms. Okay, before we start, let's share my screen. Okay, okay. Also from here, let's turn off my camera. It will be good to say. Okay. 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 Now I think it is good. Now we can start. Today we'll learn the longest remaining time fast. Okay. Let me write the name. It is longest. I mention the longest remaining time first means that LRTF. Okay, LRTF. LRTF scheduling algorithms. Okay. Okay. From here, LRTF, it's nothing but the primitive version of LJF. Okay, primitive version of LJF. LJF. Okay, previously run the LJF, longest job schedule first. Okay, it's a primitive version of LJF algorithms. Okay, previous algorithms, LJF algorithms. Also, it is exactly opposite of SRTF. Okay, SRTF is shortest remaining time first scheduling algorithms, and whether the LRTF is the longest remaining time scheduling algorithms. Okay, let's see the what is the definition. It said that among all arrived process, the process with the longest burst time or execution time will be scheduled first. Okay, longest burst time or execution time, same as the LJF, but it is a primitive version, primitive scheduling algorithms. Okay, it is, you can say it is primitive version of LJF. Means that once a process once actually your operating systems schedule a process uh, to the CPU, your CPU can preempt this process anytime. Okay, if higher priority process actually comes inside the RAM. Okay, so it is a primitive scheduling algorithm. So two things. One is the, of course, the longest burst time will gives the priority. Longest execution time is one priority, and another properties is it is a primitive. It's a primitive scheduling algorithms. Okay, it's a primitive scheduling algorithms. Okay, these are the two things. Okay, for the LRTF. Okay, so from here, what would be the problems? Actually, it's contains the similar problem here as LJF algorithms. Okay, LJF algorithms. It has also similar problem as the previous algorithms that we learned. Okay, so what is the disadvantages in here? This is a priority based algorithm because it depends on the longest execution time. Okay, longest execution time or burst time. Okay, so it is priority based algorithms. If it is priority based algorithm, there is a problems called the starvation. Starvation problems, of course, will be here. Starvation problems. And second is, we can say that convoy effect. Of course, the convoy effect problems, because a smaller process needs to wait for a long time. Okay, so this is the, of course, this kind of algorithms will be suffered by the convoy effect problems. Okay, of course, if there is a throughput, then if there is a convoy effect, throughput will be very less. This throughput will be very less. And then, of course, fourth one, what is the fourth one? Difficult to implement. Okay, the same as previous one, difficult to implement, because you need to know the execution time at the beginning. Okay, when you create the process, your operating system needs to know the total execution time that the process actually will need. Okay, but it is very difficult to calculate at the beginning. Okay, so this type of algorithm is very it's difficult to implement. Okay, Okay, this is the problems for the longest job first scheduling algorithms. So let's do one example for these algorithms, how it works. Let's say you have total, let's consider total 5 processes. Okay, 5 processes, and we compute we calculate the Gantt chart as well as the completion time, and we can calculate the turnaround time as well, that we did in our previous algorithms. Okay, here is the process ID. process ID, and here is, let's say this is the arrival time columns, and this column is for execution time, ET. Okay, the process ID, let's say here is total five process, let's say P1, P2, P3, P4, and P5. Okay, total five process in here. Now how, so let's say this arrival time 0, 1, 2, 3, 4 nanosecond. Let's consider unit of time is 4 nanosecond. Okay, 0 nanosecond, one process is P1 actually inside the RAM. After 1 nanosecond, P2 also inside the RAM. And this is, let's say, different execution time for each process. Let's say this is for 100 nanosecond. This process need 100 nanosecond. This process may require, let's say, 300 nanosecond. And then this process, let's say, 200 nanosecond. Okay. Also this process, let's say, 500 nanosecond. Here it may require, let's say, 1000 nanosecond. Okay, it's 1000 nanosecond. Okay, so how LJF will work? Let's draw the Gantt chart first. Okay, for this 5 process, let's draw the Gantt chart. Okay, okay. So this is we are talking about currently LRTF algorithm. Okay, LRTF. Okay, LRTF algorithms. Okay, so how? What is the Gantt chart? Gantt chart. Let's draw the Gantt chart first. Let's see how it looks like. At time unit 0, or we can say at 0 nanosecond, if you consider this nanosecond range time unit. So let's say at 0 nanosecond, how many processes inside the RAM? Only one process, P1. Okay, P1. Also keep in mind this LRTF is preemptive scheduling algorithm. Okay, preemptive. It can forcefully stop a process. Okay, so it is preemptive scheduling algorithms. Okay, let's consider time unit 0. How many processes inside the RAM? Only one process. Okay, only one process, P1. Okay, so P1 will be scheduled by your operating system. So P1 will be scheduled. Now what? Now after one nanosecond later, it will check. Okay, it will execute stick till 1 nanosecond. 1 nanosecond, and then what it will check? It will check that again. It will check this how many processes inside the RAM. Okay, currently how many processes inside the RAM. So P1 completes its execution for 1 nanosecond. So its remaining time is, it needs another 99 nanosecond. Okay, 99 nanosecond to complete its execution. So next, what your algorithms will check? If it is LRTF, will check this how many processes is currently inside the RAM, and among this process which needs the longest execution time, that process will give the priority. Your operating system will schedule this that algorithms. Okay, so at 1 unit 1 nanosecond time, process P1 and P2 is still inside the RAM. So P1 needs is still 99 nanosecond, but P2 needs 300 nanoseconds. So it will give the priority. It takes the largest time or longest time. So your operating system will schedule the process P2. Okay, P2 in here will be scheduled. Again, it will run, let's say, 1 nanosecond. So here is time unit is 2 nanosecond. Then after 2 nanoseconds, so it's already completed 1 nanosecond. It's completed. So it is now, it still need 199 nanoseconds to complete its execution. Okay. Now let's see that which algorithms will give the priority for next time. Okay. Let's check this how many process after 2 nanosecond, how many process inside the RAM. Okay. So here you see that after 2 nanosecond later, process P1, P2, P3 inside the RAM. Okay, because this P3 is arrival time at 2 nanoseconds. So after 2 nanoseconds, P3 also inside the RAM. Now next, what your operating system will check among this process, three process which needs the longest burst time or execution time. Okay, here P3 needs 200 nanoseconds. So, oh, sorry, there is 300. P2 needs 300. So still it actually needs 299. Sorry, it's 300 nanoseconds, not 200. So this algorithms need. So this algorithm need is still 299, 300. It's execute for 1 nanosecond. So still needs 299 nanosecond of time. Okay. So next, what's it will do from this process? It still P2 needs 299 nanosecond. Okay, P2 needs 299 nanosecond. So P2 will be scheduled because it takes highest burst time. P3 needs 200, P3 needs 299, P1 needs 99. So P2 is still longest. Okay, needs longest schedule, execution time. Okay, so P2 again schedule, it will run again till 1 nanosecond. So it is current time is 3 nanosecond. So here also it's 299, 98 nanosecond is still remaining. Okay, 298 execution time is still remaining for P2. Okay, now till P3. Now after 3 nanosecond, how many processes inside the RAM? Total 4 process. 1, 2, 3, 4. Till P4 also is inside the RAM. From here, you can see that which is the which needs the longest execution time. This is process P4. P4 needs 500 nanoseconds. Okay. Among this, P4 will be scheduled by your operating system, and P4 will be run, and then what it will do, it will run till 1 nanosecond. So it will be the 4 nanosecond. Okay. After 4 nanosecond, again your operating system will check. So it's run till 1 nanosecond. So it still need 499 nanosecond. Okay. 99 nanosecond. Okay. So after that, what it will do? Your operating system will do after 4 nanosecond. After 4 nanosecond, total all process inside the RAM. Okay. But among this process, process P5 needs 1000 nanosecond. It is the longest process. Okay. So your operating system will schedule this process P5. Okay. P5 will schedule, and then all process actually currently inside the RAM. So it how long it will execute? If it is executes, let's say 1 nanosecond, 1 nanosecond later it will check again. So it is 999 nanosecond. So still this is the longest processor, longest process. So still it can go till 499. Okay, still it can execute till how long? Still if it is if it is still 4, or if it can execute till another 500 nanosecond. 500 nanosecond. Okay, another 500 nanoseconds. So P5 is still execute for another 500 nanoseconds. So 5, it will be 5. Oh, sorry, 505 nanosecond in here. So then this process will be 499 nanosecond. Okay, and then what your process will operating system will do? Operating system will do will schedule the process that comes first inside the RAM. This process needs the equal burst time or execution time. So this process will execute. P4 will give the priority, and P4 will execute for the 1 nanosecond of time, and then it will be the 498. Okay, 498, and then 498. So it is 506 nanosecond. Now it is 498. Then again it will check. Then this process is a higher priority. Now this process will be scheduled by your operating system because it needs now long burst time. So it will execute for 1 nanosecond. Then this process will be 998, and also this is for P5. Here the time clock time is 5 okay. After that again it will check. So which one? Then again this process will execute. P4 will be give the schedule, and it will again it will execute for 1 nanosecond. So it will be the 497, 497. So it will be the 497 means this timetable will be 508. Okay, 508 1 nanosecond. Okay, 507 plus 1 nanosecond, 508 nanosecond, and then again it will switch to process P5 because now it is not actually longest process. Okay, longest executable process. Now process P5 will be again executable. So you know that you always switch back between process P4 and P5. Okay, until it's complete its execution till until it reaches till 298. Okay, once this process actually go to the 298 nanosecond, 298 nanosecond. Again, your actually operating system will switch the process always between process P2, P4, and P5. Okay. Once it executes for the process P2, let's see, it executes for 1 nanosecond time. It will be 297, and then it will check here. Then this process will get the priority. It will execute for 1 nanosecond, 297, and then this will be the higher actually longest. It needs the longest is execution time. So then this will be executed for 1 nanosecond. It will be 297. Okay, this is how it will be switched between these three process. So it will switch between till 99 nanosecond. When this process actually arrives at 99 nanosecond remaining time, 99 nanosecond, then again this process P1 will be scheduled because it's arrived fast, comes fast than other three processes. Okay, so this process will be scheduled, and also this process will be get the execute for 1 nanosecond, so it will be 98. Then your operating system will check, and then this is not a actually higher priority process. So priority it will be that process will actually get the priority to get the CPU. So this process will execute again one. Then this process will be executed for 1 nanosecond 98. And this process will be on. This is how it will be switching until actually every process completes. Okay, so this is how a process actually you can draw. It will be very big actually Gantt chart. Okay, if you consider this kind of execution time. Okay, also it always switches between these all processes. Okay, so this is how usually a LRTF works. So let's complete these things by using, even though this is very long time we consider, let's do one simple example so that you can draw everything. Okay, you can get through everything. This is, let's say, process ID. Let's consider total 3 process. Okay, total 3 process. This is arrival time. This is execution time. This is process P1, P2, and P3. Still, you consider the LRTF algorithms. Okay, LRTF algorithms. Okay, let's see arrival time 0, 1, 2. Okay, 0, 1. 2 in here. Okay, arrival time 0 and 2. This is it needs let's say it needs 5 nanosecond. This process needs total 2 nanosecond. Here it needs total, let's say total 3 nanosecond. Okay, to execute. So let's see how your LRTF works for this scenario. Okay, so let's draw the Gantt chart. So you started a process arrival time at 0, only one process. There is no other option. The process P1 will be scheduled by your operating system, and it will execute till 1 nanosecond. So its remaining time is now 4 nanosecond. Okay, 4 nanosecond. And after 1 nanosecond, how many process? 2 process inside the CPU. Process P2, P1, and P2. So P2 needs 2 nanosecond, and P1 still needs 4 nanosecond. So actually P1 needs the longest execution time or burst time. So again P1 will be scheduled for 1 nanosecond. So here it will be the 2 nanosecond. So here remaining time is 3 nanosecond. Okay, 3 nanosecond. Okay, again now again your operating system will check. Now clock is 2 nanoseconds. So after 2 nanoseconds, how many processes inside the RAM? total 3 processes inside the RAM. So among this process, which one will get the priority? That 2 process needs the same execution time. So this process will be scheduled for 1 nanosecond again, P1, and then clock time will be 3 nanosecond, and then its remaining time is now currently 2 nanosecond. So after that, uh, after that again it will check this which process needs the longest burst time. So now process P3 needs 3 nanosecond. So P3 will be scheduled and it will be run again till 4 nanosecond here. So it now is 2 nano, its remaining time is 2 nanosecond. And then again, your operating system will check this which process needs more. So all 3 processes need the 2 nanosecond. So if you consider that the process that arrive first will be scheduled, so this P1 will get the priority. So it will P1, and then clock is 5 in here, and then it needs 1 nanosecond more, and then again it will check switch back from this 3. This 2 is equal, so this one will get the priority P2. P2 will be execute for 1 nanosecond, so its remaining time is 1 nanosecond, and then here is 6. So again it will check. Now again P3 will be gets the priority. So P3, and it will be here is 7, and P3 needs another 1 nanosecond. Okay, P3 needs another 1 nanosecond. Now all 3 processes needs the same time. So P1 will get the priority. P1 gets the priority. It will run 1 nanosecond. So here clock time is 8. So it completes the execution. And then P2 will get the priority. P2 will be execute for 1 nanosecond, completes, and P3, then 1 nanosecond, P3 completes the execution. Okay. From here you can calculate the completion time or turnaround time. Okay. Let's see what is the completion time in here. In this situation, you can see or take a note in here. The completion time is nothing but the completion time at which point your process actually completes its execution. From this Gantt chart, you can get it. Okay, process P3 at 8, 10, at 10, so 10 in here, and process P2 at 9, and also process P1 at 8. Okay, so this is, let's say this is the CT. Okay, actually this is CT. So completion time is here. Okay, CT. Now we can calculate the turnaround time as well, TAT. Okay, turn around time. Okay, turn around time nothing but completion time minus arrival time. Okay, here is 8 minus 0, arrival time is 0, so 8. Here is 9 minus 1, completion time is 6, 8, and 10 minus 2, completion time is 8. Okay, turnaround time is 8. Okay. Okay, so this is the scenario for LRTF algorithms. Okay. So, do you have any questions regarding LRTF or LJF? Okay. Okay, so if you do not have question, let's move forward. Okay. Our next algorithm is priority-based scheduling algorithms. Okay, we'll talk about priority-based scheduling algorithms. Okay, let's see what is the priority-based scheduling algorithms we're talking about. We'll talk about now. Let me change this color. This one is good. It is priority based scheduling algorithms. Okay, priority based scheduling algorithm. So far you know that you consider some algorithm. This is also these are the priority based algorithms. Kind of this kind of you know that LJF, LRTF, LJF, and SRTF is priority based algorithm. Depends on the execution time. But when you talk about the only the priority-based scheduling algorithms, you need to actually explicitly define the priority number for each process. Okay, when when you when your operating system create a process, it's actually set a priority number for a specific process. Okay, these are priority-based algorithms. Mm. This is the actually priority-based algorithm. Also, these algorithms can be preemptive as well as the non-preemptive as well. Okay, here is one thing, not only the process ID. Okay, when your operating systems generate a process, there is two things. One is the process ID. Also, beside this process ID, your operating system had a priority number. Okay, okay, priority number. This is the difference. Okay, than other algorithms. Okay, here your operating system actually had the priority number for this specific process. Okay, so in this case, you just explicitly define a priority number for a specific process. Okay, so priority, and then of course the arrival time in here, and also execution time in here. Okay, it can be priority based algorithm can be two types, same as previous. One is the non-preemptive. One is non-preemptive, another is preemptive. Okay. Okay, these two types in priority based algorithm can be two types. One is the preemptive based, another is non-preemptive based priority based scheduling algorithms. Okay. So from here, let's consider one example. Then it will be, I think, more clear. Let's say we have total, let's say 5 processes. Okay, P1 is a process ID, P2, P3, P4, and P5. Okay, these are the process. This is the total 5 process, and from here, let's say your operating systems at the priority number for process P1, let's say 5, here is let's say 2, and let's say 10, 7, 9. It's kind of like this. And then arrival time, let's say 0, 1, 2, 3, 4. Okay. So let's consider this is non-preemptive. At first, we check this non-preemptive priority-based scheduling algorithms. Priority-based scheduling algorithm. Let's see how it works. This priority number, you can take a note in here. The priority numbers, because this is important concept for priority-based algorithms. The priority number can be actually this priority. It depends. Priority highest number can be the actually highest priority, or lowest number can be the highest priority. Okay, it depends on how actually you implement the algorithm. So the priority based algorithm, it is kind of simple. I think simple concept. Okay, you may when you define this algorithm, okay, this when the number is high, that means that highest priority, or you can see that when number is actually lowest, it is the highest priority. Okay, let's say if priority number is 1, then it is highest. If it is 100, then it is lowest. Or you can say highest is 100, and then lowest is 1. Okay, either way is fine. Okay, let's consider here the lowest is high, low. When priority number is low priority, consider 1 is the highest priority, and then so on. Okay, then so on. Okay, so consider the low number is the highest priority. Okay, so let's consider highest low number considered as the highest priority. Let's draw the Gantt chart. Also, it is we'll consider here the preemptive, non-preemptive scheduling algorithms. Okay, once your operating system schedule a process, your computer CPU cannot preempt the process. Okay, this is the non-preemptive. Of course, these two concepts is very important. Okay, also for your exam as well, non-preemptive and preemptive scheduling algorithms. Okay, concept. Okay, these are the two, you know that we frequently use these two terms, non-preemptive and preemptive. Okay, here you can see that if you go for a Gantt chart, this is start from zero. Of course, always start from zero, Gantt chart, because time will start from zero, and then okay, let me here give some execution time. Okay, let's say it needs 10 nanosecond. Let's say this needs 20, and then this needs like 5. This needs, let's say, 10, and this 5 nanosecond of execution time. Okay, and if it is considered the nanosecond time, okay, or microsecond, whatever you want, it's fine. Okay, after so parity based algorithm, one you need to check this arrival time. Okay, at time zero, your operating system need to check this how many process inside the RAM, and it will check only one process inside the RAM at time unit 0. Okay, and the process P1. So your operating system actually it doesn't have any other choice. Okay, it will just schedule the process P1, or so it is non-preemptive. So process P1, once you schedule the process P1, it will run until it completes its execution. So it takes total 10 nanosecond. Okay, here to 10 nanosecond, it will complete its execution. Okay, so after 10 nanosecond, how many processes in the RAM? So this process completes its execution now. So now we see that this process arrives at time unit 1, this 2, this is 3, this is 4. So all process is currently now inside the RAM. Okay, P2, P3, P4, and P5. Okay, among this process, which one will get the priority? The lowest, we consider the lowest number as the highest priority. So process P2 will get the priority, the lowest number. Okay, P2. Here is 10, here is 7, here is 9. Okay, so process P2 will get the priority. Operating system will schedule the process P2. Okay, P2 needs how long time? It needs total 20 nanosecond. So it will be scheduled, and then it will run till 20 nanoseconds. So it will be 30 in here. It completes in here at 30. Okay, 30 times the unit. Okay, so after that, which process will be now this completes this execution. Sorry, this process completes its execution. This is process P2. Okay, this is process P2. P2 completes its execution. Okay, now P3, here is priority 10, 7, 9, 9. So 7 will get the priority. Now P4 will be actually gets the priority, and it will run till 10 nanosecond. So 10 plus 30 is 40. At 40, it will complete its execution. Okay. Next process. So that one is done. So we have total 2 process, P3 and P5. Okay, this is these 2 inside the CPU currently. P3's number is 10 and P5 number is 9. So 9 will be actually scheduled by your operating system. So process P5, and it will run till 15 nanosecond. It is 15. So 40 plus 50, it will complete the 55 time unit. Now process P5 is done. P5 is done. Only process P3. Then P3 needs 5 nanosecond time. Complete the execution. So P3 will be here. So 55 plus 5 is nothing but 60. At 60, it will complete its execution. Okay. From here, you can calculate the completion time as usual, same as the previous. You can compute the CT and TAT. This is two very important parameter to calculate. CT is very easy. Also, TAT, these two is very easy to calculate once you get the Gantt chart. Okay. Once you can draw this Gantt chart, then you can easily calculate the CT. Completion time, you just go through this way. P3 completed 60 time in the 60 nanosecond if you consider this time nanosecond 60. So here is P3 60. And then you'll find this P5. Okay, P5 at 55. So P5 completes its execution at 55. Sorry, in here 55. Then here is P4. P4 completes its execution at 40. And then your P2 completes in here at 30. And then P1 completes at 10. Okay, 10. Okay, turnaround time is nothing but the CT minus 80. 80 is 0, CT is 10. So 10 minus 0, 10. Okay, 30 minus here is when it's arrived, it was 1. Arrival time was 1. So 30 minus 1 is nothing but 29. 60 minus 2, 58. 40 minus 3 is 37. 55 minus 4 is 51. Okay, this is the turnaround time of a process. Okay. Okay, so it is very easy. Your computer, your operating system, once actually you create a new process, your operating system will set a priority number. Okay, by using this priority number, your operating system then schedule the CPU for a specific process. Okay. Okay, these are priority based scheduling algorithms. If you consider the non-preemptive here, we consider the non-preemptive scheduling algorithms. Please keep in mind here priority based can be also two types. One is preemptive, non-preemptive. Another is preemptive. Okay, this is the example for priority based example for this type example that we already here I showed you. It's priority based non-preemptive. Okay, non-preemptive scheduling algorithms. Okay, scheduling algorithms. Okay, this is the example of priority based non-preemptive scheduling algorithms. So let's take another example for priority based preemptive scheduling algorithm. Then let's check this how it looks like. Okay, let's check one example for priority based preemptive scheduling algorithms. Okay, priority based preemptive scheduling algorithms. Okay, algorithms. What is the priority based preemptive scheduling algorithms? Let's draw again our table. Like we have total, let's say consider total 3 process. It will be easy to compute the Gantt chart. So this is our, let's say this is our process ID, process ID, and process ID P1, P2, and P3. And next is priority number. And here you calculate, here is the arrival time, and there is total execution time or ET. Okay, ET. Let's say priority. We'll consider the highest priority is for the for lowest number will get the highest priority. Let's say this priority. Let's say priority number is 18. This for priority number is 2. Now 1. Let's say 1. This priority number is, let's say, 10. Okay, these are the 3 process. Also it's arrival 0, 1 to this order. it needs execution time, let's say 3 nanosecond. It needs, let's say 2 nanosecond. It needs, let's say 1 nanosecond. Okay, these are the priority. These are the execution time for 3 processes. Okay, please take a note. This is priority based primitive. Okay, primitive scheduling algorithms. Now let's check the check the Gantt chart first in here, how it looks like. Here is our Gantt chart. Okay, Gantt chart. So as usual, Gantt chart will start from 0. So at 0 time unit, how many processes at the RAM? At 0 time unit. So at 0 time unit, your operating system will check this, how many processes is currently available inside the RAM. Here is process P1. At 0 time, it is available inside the RAM. So P1 will be scheduled by the operating system, and it will execute till 1 nanosecond. 1 nanosecond, then the timing is 1. So remaining time for this process is 2 nanosecond. 2 nanosecond. It needs still 2 nanosecond. Okay, to complete this execution. Okay, 2 nanosecond still it needs, and then your operating system will check this. Now, how many processes inside the RAM? After 1 nanosecond, this process already arrived. This is not arrived because it will arrive at 2 time unit 2. If it is nanosecond, after time unit 2 nanosecond. Okay, now 2 process P1 and P2 inside the RAM. Okay, let's see among this process, P1's priority number is 18 and P2's priority number is 1. So here you consider the lowest number actually gets the highest priority. So P1 will, P2 is currently the highest priority. So what CPU will do? CPU will stop the process P1. CPU will print the process P1, and your operating system will execute the process P2. Okay, execute the process P2, and then it will complete its execution 1 nanosecond. So 1 plus 1 is 2 nanosecond now. Clock is in 2 nanosecond. So after 2 nanosecond, again, your operating system will check that how many process is currently inside the RAM. So it will check, and then it will find this all process P1 after 2 nanosecond, process P3 also inside the RAM. So P1, P2, P3, all 3 process is currently inside the RAM. So what it will do? It will check this priority number. Okay, priority number process P1 is 18, P2 is 1, and P3 is 10. So still P2 is highest priority. So P2 will complete its execution. Okay, no worries. Now all processing inside the RAM, you don't your operating you don't need to check the process right now. Your all process is currently inside the RAM. So P2 is highest among this process. P2 is highest. So P2 already completes 1 nanosecond. Okay, now 1 nanosecond is left. Okay, now again P2 will be scheduled, and it will complete its execution at 3. At 3, it is done. It is done. It's completes the execution, and then it will check the switch process if it gets the priority. P3 is highest priority. Highest priority number is 10. So it will be scheduled by your operating system. So P3 will be scheduled in here, and it will complete 1 nanosecond. And also this process needs also 1 nanosecond for to complete its execution. So process P3 is done. Now we have only one process, is process P1. P1 needs still 2 nanosecond, okay, to complete its execution. So P1 will be scheduled, and it needs total 2 nanoseconds. So at 6, it will complete its execution. Okay. So this is the Gantt chart for this process. Okay, for this 3 process, if you consider the priority based primitive scheduling algorithms. Okay, and from here you can also calculate the completion time as well as the turnaround time, and also waiting time if you want. Let's calculate all three parameters in here. Completion time. We also calculate the TAT time. Also, we can calculate the waiting time. Okay, WT waiting time. Let's see how it looks like. Completion time is nothing but where or at which stage a process completes. Okay, so here process P1 completes at 6 time unit, 6 nanoseconds, and process P3 completes at P3 at 4. So process P3 at 4 and process P2 at 3. This is the completion time. Okay, once you actually calculate the complete the Gantt chart, then it is easy to compute the completion time. So from this Gantt chart, you just take these parameters and you can fill up the completion time. Okay, for each process. And next, you can compute the turnaround time. Similarly, turnaround time is nothing but CT minus AT, completion time minus arrival time. 6 minus 0, here is 6 minus 0, it's 6. 3 minus 1 is 2. 4 minus 2 is 2. Okay, this is the turnaround time for each process. Also, next we want to calculate the waiting time. Waiting time. How to calculate the waiting time? We know this another formula for TAT is nothing but turnaround time is nothing but execution time or burst time. Let me write in here. This you already know about this. This turnaround time is nothing but execution time plus IO time plus waiting time. Okay, this is nothing but also this one is nothing but completion time minus arrival time. Okay, turnaround time is actually, it means that how long your process actually reside inside the RAM or inside the memory. This is the turnaround time. Okay, how long a process remains actually inside the memory. Okay, during its execution. Okay, this is the turnaround time. Okay, so from here, let's consider this. No process actually use the IO. No process use the IO. So IO time is 0. If it is 0, then waiting time is execution time minus TAT minus execution time. Okay, waiting time is TAT minus ET. Okay, so TAT here is TAT minus ET execution time in here. Okay, so 6 minus 3 is 3. 2 minus 2 is 0. 2 minus 1. Okay, 2 minus 1 is 1. Okay, this is the waiting time. Okay, this is the waiting time for this process. Okay, so we learn the priority based preemptive and also priority based non-preemptive scheduling algorithms. What is the different here? Different here that here you don't need to consider the execution time of a process. Okay, here your operating system sets the priority number. Your operating system or whatever your algorithms you use, your operating system actually set a priority numbers. Okay, for a particular process when it creates a process. Okay, your operating system set a priority numbers. Okay, based on these priority numbers, then your operating system also schedule the process as well. Okay, so here you can see that priority number, your operating systems. This is your operating system's choice. Of course, inside your operating system, we will actually use some algorithms as well to set the priority for process. Okay, so from here you can realize that this is even though this is priority based algorithms, but it is not it is not actually kind of it is not difficult to actually implement because your operating systems have this priority number, and this priority number doesn't depends on the execution time. Your operating system doesn't need to calculate the total execution time of a process. Okay, actually that needs for LJF, also LJF, SRTF, and also LRTF. Okay, so this priority number set by your operating system. So it is not very difficult to implement. Okay, in this sense, we can say. Also, mm, also it may suffer from this distribution because it is priority. So your operating system, let's say uh, your operating system currently sets the priority number for process P1, P2, and P3. Okay, it says the priority number for process P1 is 100. Okay, then P2 is for let's say 1, and P3 is for 2. Okay, and then what's your from here which process will get the priority? P1. Okay, P1 will be executed by the CPU, and by this time let's say process P3 also creates it set the priority number 5. P6 also, let's say it's 4, and P7, let's say it's priority number 10. So all newly created process will get the priority to actually get the CPU. Okay, let's say now you can see this process P1 actually is in a trap. Okay, it doesn't know when actually it will get the CPU. Okay, so it may wait for undefinite time. Okay, undefinite time. We don't know that when P1 will get the CPU. So this algorithm also may suffer by the starvation problems. Okay, even though it is not also convoy effect. Also convoy effect can be in here. Convoy effect, even let's say because this priority, if it is doesn't consider any execution time, let's say a process needs to complete 2000 nanoseconds. Somehow your operating systems uh, actually gives the priority number for this two process, and then you create again new process. Let's say it needs only 2 nanoseconds. Okay, your operating system then actually it's your operating system decide that okay, this process will get the priority number 2. Okay, so this process will get the priority, and operating system will execute that one. Even though here is only very small amount time is required to complete this process, but this process needs to wait until this process completes its execution. So here also a smaller process may wait for a long time. Okay. Okay, so this method also may affect by the convoy effect problems. Okay, starvation problems, convoy effect problems is in here, but implement is not difficult, like SRTF, LJF, also LRTF. Okay, okay. So do you have any questions or comment for 2 days that we discussed already? Okay, so if you have do not if you do not have any questions, okay, we can stop here today and see you next class, and have a good weekend. See you next class.